Hello everyone, we are group 3 and we are going to present our demonstration on diagnosis of different heart rhythms from simulated ECG signal today. Electrophysiology of the human heart is as illustrated in the figure, showing different waveforms for each of these specialized cells. ECG refers to the recording of electrical activity of the heart using electrodes. The voltage of the ECG signal can vary depending on the location of the electrodes placed on the body.
Tachycardia is one of the conditions where the heart beats at faster rate than the normal. And talking about the different type of heart rhythms, atrial tachycardia is one of them. It is an abnormal heart rhythm where the upper chamber of the heart beats quickly. The heart rate is greater than 100 beats per minute. Three different types of P waveform is observed, and the QRS is in normal pattern. The second one is ventricular tachycardia. It is an arrhythmia where lower chamber of the heart beats quickly. The heart rate lies in between 120 to 150 beats per minute, and generally no P waveform is observed, and the QRS rhythm is regular. The third one is junctional tachycardia. It is the type of racing pulse caused by the problem in the area between upper and lower chambers of the heart. The heart rate lies in between 100 to 180 range. The P waveform is usually present before or during or after the QRS complex, and the QRS pattern is in normal condition.
ECG signal has been simulated by LabVIEW. Based on the simulated ECG signal, the other task has been achieved: adding noise to the simulated signal 50 Hz, spectrum analysis, filtering raw signals. Features are important as they contain specific information that is hidden under the raw electrical signal. Time domain features and frequency domain features can be extracted. Using the filter data and the features to use the simulated data to classify different heart rhythms.
The simulation of ECG signal can be done by using LabVIEW. Here, the ECG signal was considered as an input, and the configuration settings were done as shown in the screen by setting various parameters. The graphs obtained after setting the configuration are as shown. It was done for normal ECG waveform, atrial tachycardia, junctional tachycardia, and ventricular tachycardia. And from all the obtained graphs, it is seen clearly that the PQRS complex for each of the waveform is different. And now, talking about the signal processing, frequency spectrum of unfiltered signal is as shown in the graph, where the noise of 50 Hz was identified, and in order to remove the unwanted noise, bandstop filter was used, and after the application of bandstop filter, the frequency spectrum of filtered signal was obtained as shown.
Short-term Fourier transform is segmenting the signal into narrow time intervals so as to enter the signals to be stationary. The mathematical formula is as shown in the screen, where t dash is the time parameter, u is the frequency parameter, f of t is the signals to be analyzed, w is the windowing function, t minus t dash is centered at t equals to t dash. STFT is computed for each window centered as t is equal to t dash. A window function of finite length is chosen. The window is placed on top of the signal at t equal to 0. The signal is then truncated using this window. Fourier transform is computed for these truncated signals, providing simultaneous time and frequency information. As you can see, majority of the signal frequency is below 50 Hz for all ECG signals, which we also found in the ECG frequency spectrum. Different types of ECG signals can be differentiated based on the respective STFT spectrograms. It is important to note that normal and junctional ECG signals have similar STFT spectrograms. Wavelets are oscillating functions whose energy is concentrated in time to better represent transient and non-stationary signals. Two parameters are incorporated with respect to time: translation and scaling. Discrete wavelet transform discretizes the transformed 2D function x of t to the chosen sample grid. Diaric sampling s equal to 2 to the power of minus j, and translation is equal to k2 to the power of minus j. Continuous wavelet transformation is the convolution between the signal x of t and a filter with impulse response I of minus t by s. It can be viewed as a type of bandpass analysis where the scaling parameter S modifies the center frequency and the bandwidth of a bandpass filter. Based on the STFT spectrogram and CWT scalograms, the frequency for all ECG signals have been obtained below 50 Hz. We realized that the normal and junctional have a lot of similarities and features for classification and were selected based on these evaluations.
Greetings everyone, I'm Buddy and I'm going to talk about the features that were extracted for classification along with the classification model that we developed for this project. Next. Now, one of the features which we extracted were based on discrete wavelet transform. In order to extract DWT based features, first decomposition filters were obtained using BioR 3.5 wavelet using the course as shown in the screen. After that, the approximation coefficients and detailed coefficients were obtained. From these approximation coefficients, which are highlighted in blue, would be used in the classification model. Next. Another features that we considered were root mean square values. Now, in order to get root mean square values, the ECG signals were first divided into 30 equal parts. For each part, we take out the RMS value. These RMS values were then put in an array. The array which is highlighted in blue would be then used in the classification model. Next. Another feature that we considered was ratio of maximum value of the ECG signal to the minimum value of the ECG signal. This was considering the fact that different types of ECG signals have different PQRS complex. So the ratio would be able to provide us with good classification. Next. Now the classification model. The classification was done using classification learner toolbox in MATLAB. For each ECG signal type, we used 5 signals for training and 2 for testing. The type of classification that we used were decision tree models and support vector machines, SVM. Support vector machines were able to provide us with a very good classification. The highest accuracy that we were able to achieve were 100% for all kind of features. Now, this is important to note that this accuracy was achieved using the signals which were simulated. If we were to use actual signals, the accuracy might decrease a bit, but it will still be within acceptable range. Now I'm going to show you the demonstration using LabVIEW and MATLAB. So in MATLAB, in LabVIEW, first I am gonna first we simulated the ECG signals using simulate ECG VI. In this one, this is the configuration that which we used, and we also put in the power noise, which is at 50 Hertz, into the ECG signal. After simulating these signals, we exported them to MATLAB using this VI. Now in MATLAB, once we import the signals that we generated in LabVIEW, we first did the signal filtration. I'm going to show you now. As you can see, as it was discussed earlier, we removed the 50 Hertz frequency from the simulated ECG signals and filtered it using a band stop filter to get this filtered frequency spectrum. We did this for all the signals that we simulated. After that, for evaluation, signal evaluation, we did STFT and CWT analysis. For that, I'm going to show you for the spectrums, the figures for one signal. So this is the STFT for STFT spectrogram for normal ECG, and CWT scalogram for normal ECG. The details and the features and the evaluations which we have discussed in the presentations, and we were going to explain it more in the report. Now, after we extracted the features from the signals using the method which I discussed in my presentation, it is important that we format them or arrange appropriately so that these can be imported into the classification learner toolbox. So for that, we did a formatting script. This is for RMS features. After that, we imported those formatted features into the classification learner toolbox, and then we trained them using the appropriate models. As you can see, for decision tree model, we got 75% accuracy, and for various SVM models, we got all 100% accuracies. Now, once we are satisfied with the accuracy we achieved, we exported the model into MATLAB again. And then we try to test our trained model with a fresh signal. So I'm going to demonstrate the testing out here. So I'm going to put an ECG signal, which was not actually given to the trained model, and this trained model should be able to identify it correctly. As you can see, it's able to classify or identify it appropriately. So this is the end of our demonstration. Thank you very much. All right. I'm going to stop it.